In this video, we will be designing a combinational logic using programmable array logic, and here is a second example. The link for the first example is posted in the description box. So here the question is to design a combinational circuit for all these four functions and implement that using programmable array logic. So the first step is to create a truth table. So these are the expressions that is given, there is input function given. So when you look into the minterms, it starts at 0. We have 1, 2, 3, 4, 5, 6 until 7. Maximum we have from 0 to 7. So 0 to 7 in the sense we have only 8 minterms. If we have only 8 minterms, then it should be something like 2 power 3, where 3 is the input number of bits. Therefore, how many input variables we have? X, Y, Z. The same X, Y, Z is been given here. We have 3 variables, X, Y and Z. So X, Y and Z. If the variables have been given here, it is very easy for us to identify. In case if the variables are not given, then we can identify using this technique where we have to find out the minimum minterm and the maximum minterm available. So how many number of minterms are there in total? So which is equal to 2 power 3. So 2 power 3 is 8. Therefore 3 is the total number of inputs. So we have X, Y and Z right now. So if we have 3 input variables, then it should range from 0, 0, 0 up to 1, 1, 1. So 0, 0, 0, 0, 0, 1, 0, 1, 0 up to 1, 1, 1. We have listed all possible minterm combinations. Now we have the function A. So what is the function A? A holds minterms 1, 2, 4 and 6. 0, 1, 2, we don't have 3, we have 4, we don't have 5, we have 6 and we don't have 7. So for the rest of the function, we are marking 0. And in the same way, we have to do it for B, C and D. So when we assume B is equal to, what are all the minterms? 0, 1, 6 and 7. So 0, 1, we don't have 2, 3, 4, 5, we have 6 and 7. Similarly, we can do the same procedure for C and D. The same thing is being done and the table is being filled. So when we assume D has minterms 1, 2, 3, 5 and 7. So 1, 2, 3, 5 and 7. For the rest, 0 is marked. Similarly, for C we have only 2 and 6 and the rest are 0. So the truth table is done. This is step 1. Next, step 2 is to use a KMap and find out the expression for A, B, C and D. Let us do it one by one. Let us first start with finding out the expression for A. How many input variables we have? We have X, Y, Z, 3. Therefore, KMap also can be a 3 variable KMap having variables X, Y and Z. So right now X can be only 0, 1, Y can be 0, YZ can be 0, 0, 0, 1, 1, 1 and 1, 0. So when we try to plot all these minterms inside, at 0th location we have 0, we have 1, so 1, at 2 we have 1, so at 2 we have 1, at 3 we have 0, and 4, 5, 6, 7, 1, 0, 1, 0. So 1, 0, 1, 0. So our KMap, we have written all the combinations here. Now we have to group. So in order to group, this is one possible grouping of taking these two variables together, and the highlighted with green color, this forms one group, and this one cannot be grouped, so we are forming it separately. When we consider these two corners, X variable is common to both these minterms, therefore we are writing X. When we consider column wise, we have 0, 0 and 1, 0, which is nothing but Y and Z. Z is common, which is nothing but in form of 0, therefore we can write Z bar. So X, Z bar becomes the expression for this group. And similarly for the one highlighted in green color, there is no variable X is not common because here we have 0, here we have 1. But when we look into column wise, 1, 0, Y, Z bar is common to these two minterms, therefore Y and Z bar. When we consider this one alone, we have X bar, Y bar, Z. X bar, Y bar, Z. Therefore, x bar y bar z plus x z bar plus y z bar. This becomes the expression for A. In the same way we have to do for B also. It is 1 1 0 0. So 1 1 0 0 followed by 0 0 1 1 0 0 1 1. So this is one possibility of group. This is another possibility of group. When you write expression, x is common, therefore x. When we compare these two, it is 1 1 and 1 0, which is nothing but yz. So y is common. So this becomes xy. Similarly, when you compare this group, x bar, so x bar. When you compare 0 0 0 1, it is y bar z. So y bar is common. So y bar, x bar, y bar. So x bar, y bar plus xy becomes the expression for B. Similarly, we have to do for C. 0 0 1 0, 0 0 1 0, 0 0 1 0, 0 0 1 0. We can try to group these ones alone. That is the only possibility. X cannot be written because it is 0 and 1, it is varying. Therefore, it is possible to write only 1 0. So, if it is yz, 1 0. Therefore, this could be yn z bar because for z it is 0. So, yn z bar. So, C will be equal to yn z bar. What about D? 0 1 1 1. So, 0 1 1 1. Similarly, 0 1 0 1, 0 1 0 1. So, when we look into, there is two possibility of grouping. One is to group all these 4 ones together and the rest of ones with this green color grouping. So, when we write expression for this brown grouping, 0 1, so we cannot write x. When we compare these two, yz will be 0 1 and 1 1. Z is common, therefore we are writing z. When we look into for this, x bar is common, therefore x bar. When we look into column wise, it is 1 1 1 0 for y and z. So y is common, therefore we are writing y, x bar y. Therefore D is equal to x bar y plus z. Therefore we have written expressions for A, B, C and D. The third step is to create a PAL program table. So right now we have the expression A equal to x bar y bar z. So these are the product terms. We have to take this product term into the table. So first is x bar y bar z. So we are taking x bar y bar z, then x z bar, x z bar and y z bar, y z bar. And do we have any of these three terms in this expression somewhere? X z bar we don't have, y z bar, y z bar we have here. Therefore this can be neglected because we have same y z bar which is already been written. So no issues. Similarly, next we have to find x bar y bar. So x bar y bar. Next is xy, xy. Similarly, we have to check whether these two terms are available anywhere here. It is not there. And we have already neglected yz bar because already we have yz bar here and we have written. Next we have to jump to the next expression for D, x bar y plus z. So x bar y and z. So these are the maximum product terms. So we have listed all possible product terms without any repetition. So now we have two columns, one for inputs and other for outputs. What are all the inputs? We know that inputs are x, y and z. Okay. So what are all variables that we have? We have instead of x, we have x complement, therefore 0. We have y complement, therefore 0. We have z as such, therefore 1. Do we have x here? Yes, therefore 1. Do we have y? No, therefore mark with a hyphen. For sz, it is in complement form, therefore 0. We don't have x, therefore hyphen. We have y as such, therefore 1. We have z in its complements form, therefore 0. Here we have x bar, y bar. So 0, 0. We don't have z, therefore it is a hyphen. We have x and y as such and we don't have z. We have x bar, therefore x complement means 0. We have just y as such, so 1. We don't have the term z, therefore hyphen. And similarly here we have only z. We don't have the rest of the terms x and y. So input table is completed. Now we have to move to the output table. What are all the outputs? We know that the function was given something like this, a of x comma y comma z. Similarly b of x comma y comma z. So those a, b, c, d are the outputs for which we have found the expression also. So a, b, c, d. So when we look into a, for the expression a, What are all the terms we have? X bar, y bar, z is one product term. So x bar, y bar, z we have, therefore mark with 1. What is the other product term? X, z bar. So x, z bar, we need x, z bar, and we need y, z bar. We need y, z bar. So mark with 1. And we don't want rest of the terms, therefore we are marking with hyphen. Similarly for B, what are all the terms we need? We need x complement, y complement plus x and y. So 1 and 1 for x bar, y bar and xy. Rest of the terms we don't want. Similarly C, we need y, z bar. So y, z bar is only term. For rest of the terms we are marking hyphen. For D, we need x bar, y and z. So x bar, y and z, and we are marking hyphen for rest of the terms. And all these logics are implemented using true form, direct form only. We are not using any of the complement form. Therefore, we are marking true for every A, B, C, D output. So, right now PAL program table is done. Directly we have to jump into implementation now. Now we have to implement the same logic using a PAL. So, we know that the OR structures are already programmed. Only AND structures can be programmed. So, right now we have product term x bar, y bar and z, x, z bar and y, z bar. These three together gives us the output A. So, for output A, we need three product terms that will give you x bar, y bar, z, x, z bar and y, z bar. So, we need three AND gates. So, x bar, y bar and z. Similarly, we need x and z bar. So, x and z bar. We need y and z bar. So, y and z bar. All these three terms must be ORed because expression for A is equal to x bar, y bar, z plus x, z bar plus y, z bar. We have to use an OR gate in order to OR these three product terms. So, our expression for A is implemented. And here the x complement, y complement, z and z complement are the, we have three inputs, therefore three possibilities x, y, z plus in its complement form. So, totally we will have 6 wires. All these explanations have been given in the previous example also. You can refer to that video. And now we have to go for implementing B. When we work on with B, what are all the terms we have? X bar, y bar and xy, because we know that B is equal to x bar, y bar plus x and y. So, we need one product term and two product term. Therefore, we need two AND gates and then we have to OR these two product term together. Therefore, we have an OR gate. So, what are the product term that this particular AND gate is going to give you? X bar and y bar. Another AND gate must give you x and y. So, x bar, y bar. Another AND gate should give x and y. These two terms must be OR together in order to obtain B. In the same way, we have to do C. C has y and z bar. Therefore, y and z bar. And now C is done. Next, we have to move on to D. D has x bar, y and z. So, D is equal to x bar, y plus z. So, x bar, y, we have z. X bar, y, and for this gate, we have z. With these two terms must be ORed in order to obtain z. That's it. So, all the expressions A, B, C, D that we derived are implemented using a PAL. For better clarity, the unprogrammed AND gates are not shown in the figures. I hope the explanation was clear. Thanks for watching the video.